The universe has a skeleton, and for the first time in human history, we can see it. Not just hints of it, not simulations, the actual, staggering architecture of everything that exists. And what James Webb found when it looked at it will genuinely change how you see the night sky forever. Here's what we're dealing with. The universe is not a random scattering of galaxies floating in empty space. It is structured, organized, woven into an enormous three-dimensional web of filaments, walls, and voids, stretching across billions of light years. Astronomers call it the cosmic web, and it is, without exaggeration, the largest structure in existence. Every galaxy you've ever seen in a photograph, every nebula, every star cluster, all of it lives somewhere inside this web. The question that's haunted cosmologists for decades is, what does it actually look like? And now, thanks to the James Webb Space Telescope, we are closer to an answer than we have ever been. But here's the thing that nobody talks about. The reason the cosmic web looks the way it does goes all the way back to a fraction of a second after the Big Bang. That origin story is stranger and more beautiful than you'd expect, and we'll get there. Let's start with the basic picture. Imagine taking every galaxy in the observable universe, all 2 trillion of them, and watching them from far enough away that individual stars are invisible. What you'd see is something that looks almost biological. Long, glowing threads connecting bright nodes, vast, dark bubbles of emptiness, sheet-like walls hundreds of millions of light years across. It looks like a neural network. It looks like the inside of a sponge. It looks, honestly, like something alive. And in a sense, it is, because this structure grew. It was not placed there. It evolved over 13.8 billion years from something almost perfectly smooth into this breathtaking complexity. Now here's the part that makes this feel almost eerie. Those dark bubbles, the voids, are not empty. They're mostly empty, but they are also giant. The Booty's void alone is roughly 330 million light-years across. If the Milky Way were sitting in the center of the Booty's void, we would not have discovered any other galaxies until the 1960s. The nearest galaxy would have been so far away, it would have been nearly invisible with older instruments. Think about what that means for any civilization unlucky enough to live deep inside a void. Their entire observable sky could contain almost nothing. They might have concluded for centuries that their galaxy was the only thing in existence. But we don't live in a void. We live in a filament. The Milky Way sits in a structure called the Laniakea supercluster, which itself feeds into the broader cosmic web. And this is where James Webb changes everything. Before Webb, our maps of the cosmic web were either nearby and relatively detailed, or distant and extremely blurry.
The problem with looking far away in space is that you're also looking far back in time. The light from distant galaxies took billions of years to reach us, so you're seeing the universe as it was, not as it is. Webb's extraordinary infrared sensitivity lets it peer into that ancient light with a clarity no telescope before it could match. In 2024, researchers used Webb to observe a massive filament of galaxies stretching roughly 13.4 billion light-years from Earth, a structure forming when the universe was less than 1 billion years old. That's the cosmic web in its infancy, and it was already organizing itself, already building its skeleton. So why does it look this way? Here's where the origin story pays off. In the first fraction of a second after the Big Bang, the universe was a nearly uniform hot plasma. Nearly uniform, but not perfectly. There were tiny quantum fluctuations, microscopic ripples in density. Some regions were infinitesimally denser than others. And over hundreds of millions of years, gravity did what gravity does. It amplified those differences. Denser regions pulled in more matter. Matter flowed along paths of least resistance, draining from voids into filaments, from filaments into walls, from walls into the massive galaxy clusters that sit at the intersections, called nodes or sometimes cosmic knots. Dark matter, which doesn't interact with light but absolutely does interact gravitationally, formed the invisible scaffolding first. Ordinary matter, gas, dust, stars, you, followed that scaffolding like water running down a framework of wire. This is the perspective shift moment. The shape of the cosmic web was determined before a single star existed. The blueprint was written in quantum noise, smaller than an atom, amplified by gravity across 13 billion years into structures hundreds of millions of light years across. The arrangement of galaxies in the night sky is, in the deepest possible sense, a magnified image of quantum mechanics. The largest things in the universe grew from the smallest fluctuations imaginable. That connection, from the subatomic to the cosmic, is one of the most profound ideas in all of science. Now Webb is letting us test whether our models of this process are actually correct, and the early results are already creating tension. Some of the massive galaxy clusters Webb has found in the early universe are bigger than they should be, given how much time they had to grow. This is not necessarily a crisis for physics, but it is a flag. It suggests our models of how structure forms may be missing something. Maybe dark energy behaves differently in the early universe. Maybe there's physics we haven't accounted for. Every time Webb finds a galaxy cluster that shouldn't exist yet, it's not breaking our understanding, it's sharpening it. It's forcing us to build better maps, not just of space, but of time itself. And here is the detail that I find genuinely haunting.
When Webb maps a filament of galaxies 13 billion light-years away, the photons that hit its mirror left those galaxies before Earth existed, before the Sun existed. They've been traveling through the expanding universe for nearly the entire age of the cosmos. And when they finally land on a cold mirror floating in space a million miles from Earth, we turn their journey into an image, and we learn something about how everything came to be. That is not a small thing. That is one of the most extraordinary achievements in the history of the human species. The cosmic web is not just a map of where galaxies are. It's a record of the universe's entire history, written in the positions of matter across billions of light years. Every filament is a fossil, every void is a scar, and JWST is the most powerful tool we have ever built for reading that record. We are living in the era when the skeleton of the universe is finally coming into focus, and the more clearly we see it, the more questions it raises. Questions about dark matter, dark energy, the earliest moments after the Big Bang, and whether our models of cosmic evolution are as solid as we thought. The best discoveries Webb will ever make may still be ahead of us. If this blew your mind even a little, hit subscribe. We go deep on space science every week, and next time we're exploring something that Webb found that physicists are genuinely struggling to explain. You will not want to miss it.